All right, so those are mental lexicons. Once again, stressing that those are theoretical connections, because if we wanted to get into the idea of, well, could we map our different neural connections? Yes, you can map some neural connections, but the complexity goes off the charts very quickly. I don't know if we've talked about the magnitudes here, but we have billions of neurons that can each make thousands of connections, so there are trillions of connections you'd have to map. So for those neural maps, we can't really do it on this right scale to quantify all of that. So we can either do physical connections with no meaning, or we can do meaning and context with no physical connections. So we have to prioritize what we're interested in. But yeah, with that out of the way, this is one of my favorite topics, and this is category membership, which typically I'll give examples of stuff like this, and you've heard a few with talking about chickadees and operant conditioning. But my research is all about asking questions about how chickadees put things into categories. So I use my example. Let me double check that I don't actually have the example here. Good, okay. And again, when I mention chickadees, you don't have to know the specifics, but I do that thing where I present them with male calls, and we teach them that if you hear a male call and you hop in the feeder, you get food. So male calls are good. And then you teach them if they hear female calls and they hop in the feeder, the lights turn out. So female calls are bad. And then we say, okay, we've trained you up on these hundreds of calls, and now we're going to give you new calls from new birds that you've never heard before. If you can form a category and all male calls fall under the same umbrella, they're the same concept to you, then presenting you with new calls, you're just going to treat them like all the old calls. You would say, I've learned the rule that this category is good and that category is bad, so if you react that way, we know that you form categories. And if you are curious, chickadees can do that with their songs, but choose not to do that for their calls, which took 3+ years to learn. But they are capable of forming some categories depending on the importance of those categories. And if you want to think about why is it beneficial to form a category, for us it was, do you want to form a category of male is good and female is bad, or do you want to memorize these 500 calls? They opted for the memorizing route. But for day-to-day life, if you can form a category and learn a simple rule, that ends up saving you a lot of processing power and storage whenever you face a new thing that might fit within that category. So if you learn that green lights, regardless of what a street light looks like, whether it's vertical and yellow, vertical and black, horizontal and black, or silver, or whatever iteration we come across, if we treat them all as street lights, then we are going to respond to them all in the same way. We don't have to be exposed to them all previously. We're not then going to panic when we come to an intersection with a weirdly colored street light. We treat it the same as all the others. So we put it into a category, and we know how to respond to that category. And so this also works for when we're looking at sort of language and how we talk about things. We can label things. Humans love to put labels on things. And this is actually a behavior that you see in very young children where they like to group things based on some quality. But for our example, and this one I didn't specifically choose. One of my textbooks used birds. This one's not on me. But they said, okay, our category is bird. And we have certain defining features that relate to being a bird. And so if you visualize a generic bird, you probably see some cartoon bird shape that looks something like a robin. Sort of the long, spindly legs, round, fat body, long tail, stubby head, something like that. And so we'd say, okay, well, it has feathers, it can fly, it has wings, probably a round body shape. Those are what I think of when I think of a bird. And so a robin would absolutely fall into that. It has extra qualities, so it's also red-breasted, it has gray feathers, maybe we care about the beak color, whatever else we can think of. But it's going to tick a bunch of our boxes for those defining features of our category. We'd glance at a robin and very quickly know that it's a bird. However, if we look at, say, an atypical member of that category, and this is something that children, as they acquire language and learn all of these different items, objects in their environment, they'd see an ostrich, and they're like, okay, well, it has feathers and it has wings, but it can't fly. So does it still count? It also has longer legs and a neck than what we'd expect from our stereotypical bird. Does it still count? And so this might require asking some questions. So children would ask a lot of, what's that? And so we'd have to think about, okay, well, if we don't tick as many boxes, it's less easy to connect that to our category. Penguins pose a similar problem because while they do technically have wings and feathers, they don't look like it in the way that we normally see them. So they might even be weaker than ostriches, and especially the can't fly turns into they swim instead, might be problematic for concept formation. And so that's our logic looking at this of, does this thing belong in this category or not? And how do we decide if it belongs to that category or not? There's a couple of theories. Usually we look at what's called that theory of resemblance. And it just says that our object classification, does it belong to that category or not, is going to be mainly based on connections and representations, the qualities of whatever it is we think is typical of that category. So how many of these defining features does it have? And we can decide if that thing overlaps with our general understanding of what that concept means to us or not. And this can work with meanings as well, depending on, say, maybe how words look or how they relate conceptually. Maybe we'd put sports together under that sport heading. And you might have debates with people about, does this count as a sport or not? I've seen some of my friends love having those stupid arguments to have, where it's, does a wrap count as a sandwich or not? Or does a hot dog count as a sandwich? And stuff like that. And it's all, does it fit in this category or not? And that stereotypical member of that category that I've been kind of beating around the bush for, they also call it a prototype. And that is the most common or typical version of that word. That's what typically comes to mind when we think of that particular category. So here, for birds, pigeons might be a pretty good prototype for what we would anticipate a bird would look like. And the more un-pigeon-like they look, the harder it might be for a child to connect them to that category. And so in this situation, we have sometimes, we'll see proposals like this. Say you'd approach a child and say, all right, this is our prototype. This is our category. These things are, make up some phrase for them. We can call them circle squiggles, because kids really don't care what you call things for categories. And you'd say, okay, out of all of these, which ones would belong in the same group as this one here? And so they'd probably say that the circle counts, even though it doesn't have the squiggles, it's maybe close enough. Maybe the star counts because it's the same color, but it's the wrong shape and it doesn't have the squiggles. So we're less sure about the star. The square is the wrong color and the wrong shape, but has the squiggles. So maybe it counts. And then the triangle, we'd say for sure no, because it's the wrong color, it's the wrong shape, and it has no squiggles. And so you can ask for their reasoning if they're of an age where they can explain that, or you could just ask them to sort them into this category versus some other category and see how they divide them. There's also some neat stuff. I don't think I have it in my slides, but they do a study where they start by talking about what something has been made of. So they will have, I can't remember, it's again, they make up a term, but they have a child who has a cup and the cup is made out of tin. And so they'll tell the kid that this is a blurp and you need to go find more blurps. And if you tell them that, they'll go and find a bunch more cups in the room. And they'll bring you all the cups out of the arrangement of all of the options they have available. Whereas if the child is at a level where they've learned the word cup, and they know what a cup is, but you tell them that it's still a blurp, they assume that you're talking about some quality of the object. And so they actually tell you, or you would tell them to go get more, and they'd find things that are made out of the same material. So if tin is sort of this special material, something maybe they're not familiar with and definitely don't know the name of, they'd go find a whole bunch of tin objects in the room, or at least shiny metal objects. And that sort of predictive quality of if they know this thing, they assume you're talking about something specific, whereas if they don't know the name, they assume that you're giving them something general about that object, is consistent across a whole bunch of different cultures. So it's another one of those universal qualities, and it kind of ties into our category formation when we introduce that possibility of uncertainty and existing knowledge and things like that. But there's a whole bunch of really cool developmental studies that look at things like that, delving into how children start forming these categories, how they link concepts based on making predictions with very limited amounts of information. But it's kind of neat to see that consistency because it maybe gives us an idea that there might be something else going on with biological predispositions. All right, then our next concept here, this is a really cool one, and I feel like that's this entire lecture, but this is when we're starting to bridge that gap between language and getting into that thought component of this lecture, transitioning us over into problem-solving stuff soon enough. But this is the Sapir-Whorf hypothesis. And you might have heard it called linguistic relativity. But this is a theory that says that the structural differences in language can actually alter our perception of the environment and specifically alter our understanding of reality. Basically saying that the words that we have available to us and the concepts that our language is capable of describing ends up influencing what it is that we're capable of perceiving in the world around us. And typically there are sort of 2 or 3 main studies that they always point to when they discuss this specific hypothesis, but they like looking at things like, do you have perceptual words for colors? Or there's usually the example of how many words does your language have for snow, or certain other things. We're going to use colors though, because that's the visual that I have, but it's also a little bit easier to conceptualize. And so, in this situation, what they do is they look at people in different cultures where they speak different languages, and specifically, they're going to look at, say, languages that have, say, a dozen or more different words for the different shades of blue. In English, we have lots and lots of different ways to describe colors blue. But there are some cultures, and as per usual, I don't remember the specific name because I'm terrible with nouns and I didn't write it down, but there is one language where they technically only have 2 colors. So they describe warm colors as all in one category and cool colors all in the other category, and they don't make any distinction between those. So they wouldn't talk about blue and purple and green as different colors. They're all cool colors, so they all fall under the same label. And so what they would do in these sorts of tasks is they're going to show you a sample color, and they'll have 2 comparison colors, and they'll look at your ability to match that sample to our comparisons. Usually they'll use what's called a delayed matching to sample, which is their fancy way of saying, we flash the color on the screen, the sample, we then take it away, wait a moment, and then we show you 2 options. And you are supposed to pick the one that matches. So hopefully the slides are okay on the projector and we can see that these 2 are the same. This one is a little bit lighter and therefore different. And then they'd look at performance. How accurate are you? And does that relate to how many words your language has for the colors we're looking at? And they typically find an increase in performance in those cultures that have more words for those colors. And they would turn to that and say, aha, having more words to describe colors means that we are better capable of perceiving differences between shades of those colors. However, you might tell from my hesitation in stating things like that, this isn't necessarily as straight cut as they usually report the findings. And the example that I always use to explain this away is, what about experience? Not just from the language itself, but if you look at, say, people who have an art background versus do no art, do we then find that those who are artists and are used to paying attention to different colors are better able to discriminate between similar shades? Probably. And if we think about our categorization and how we get kids to put things in categories, well, if you imagine a kindergarten class and they hold up a block and that block is blue and they ask all the kids, what color is it? They would tell you blue. And you show them a slightly different block and ask them what color that is. All of a sudden, it's not so much that the language has all of these labels that's making you capable of seeing, but because the labels exist and you practice putting things in those labels, maybe that's playing a larger role. And for some people, that might not mean a whole lot of difference. They might say still that practicality of using those labels changes your ability to discriminate colors, and that's enough for them to say that this still holds. That's totally fine. But sometimes you always have to acknowledge that there's that possibility, that other variable that might need to be considered, and experience with that category might be really important. And yeah, you can decide, do you think that's enough to negate this hypothesis or not? It depends on who you look at. But they've done tons and tons of follow-up studies with this. And while originally they were fairly confident that this was the case, more recent research has gotten into, if it does have an effect, it's nowhere near as large as we thought it was. So we mention it because it's a neat concept and it was something that had a lot of traction, but in practicality, you can't really blame the language that you speak on, say, influencing how you can and can't think about a concept. All right, and like I said, that is a nice transition from language. We get into categories and fitting things into categories, and then we can get into how we think about solving problems, getting into that more thought-heavy framing. And so in this section, we get to start looking at what are some of the techniques that we can use when we solve problems. And I guess we should start with our what is problem solving. It's a sequential process where we go from some problem state to some desired end goal by applying some kind of strategy. So it's a pretty vague definition, but solving problems is also a fairly vague concept. And with that, we will acknowledge that we're just putting forward a couple of different ways people might approach problems. This is not an exhaustive list of how you can solve problems. But we're just saying we start off where we are in an unhappy state. We need to change some things, move some things around, do something in order to get to our happy, desired end goal state after all of our manipulations. And our ability to problem solve, our ability to go from start to end, can be dramatically affected by a whole bunch of things. So the problem itself, what is it that we're starting with and where are we ending? That can absolutely affect which kinds of strategies we might think of, which kinds of things we might try to solve the problem. Each individual might have a different way of framing or approaching a problem. So if you remember back to math classes, and maybe they give you a word problem, and you interpret those words one way, and you spend a whole bunch of time fighting with all of that information and not being quite sure what the answer is, but maybe you have a friend who interpreted the problem in a different way and found a solution really quickly and easily, your approach there, the way that you drew important information that was presented, ended up affecting your ability to solve that problem. It also affected the mechanisms you would have used to solve that problem based on which information you decided was important or not. Of course, past experience is absolutely going to play a role, and we actually get to see a little bit of a bias in past experience in an example on the next few slides. But in this case, if you encounter a problem and it's something you've solved before, you already have that solution in your back pocket. You can pull that out and use it without having to think of something new. Whereas if somebody has no experience with this area, this type of problem, any of that information, they might have to solve it in a completely new way. And with their lack of experience, they might solve it in a very inefficient way because they're sort of shooting in the dark. They have no idea where to start. We'd also want to think about general knowledge. So we can tie this to things like general intelligence or even fluid intelligence, our abilities for flexible thinking and approaching things in a creative way. But we might also include bits and pieces of information. Maybe you have a formula that you know that not everybody else knows that might relate in this situation. Or you might think of trying to think of what other abstract examples I can use. Things like maybe you understand how, it's one of those stupid train problems of you're leaving from this station and getting to that station and traveling at this rate. Maybe you know some extra background information about trains and how they travel, or something about their acceleration that you could add to your solution to make it more accurate. All of that can be involved. And then the last point here is our available strategies. That can include sometimes limitations that are stated within the problem as it's posed. So if you've ever heard one of those where they say, okay, you need to get from A to B, but you can't do this. So you would then have to use some strategy that doesn't involve that. So there's all sorts of different things that we consider, and for all of the examples we have, they each have different bits of useful information. But like I said, we have an example that we're going to start with. And so here, you can probably read it better than just listening, but you have unlimited water, you have this infinite amount of water available to you, and you need to measure exactly 100 ounces, because I borrowed this from an American text, and you need 100 ounces of water in this specific cup. And these are what you have available to you to scoop out known amounts of water. And so if we look at it, we have 127 ounces, 21, and 3. So if we need exactly 100, maybe we're going to fill A once and put that in the target cup, and then we're going to fill B from the target cup and remove 21 ounces, getting us down to 106, and then we'll take away 2 of C. So we add A, take away B, and take away 2 of C, and that gets us our exactly 100. And so that's our solution. We came up with that. I'm sure you guys got there too. And then we have a new example. We say, okay, now we have different sized cups. Still unlimited water available to us. Target cup, we need exactly 20 ounces. What are we going to do? And you might look at it and go, okay, well, 1 of A, take away 1 of B, and take away 2 of C also solves our problem. And because we just solved a problem with that, that's the first thing we try. But you might also have noticed that if we just add B and take away C, we also solve the problem. So our first solution was not wrong. We did get there in the end, but it was not the most efficient solution. So our prior experience can actually make us stuck in this idea of this is how I should solve it. So it might prevent us from finding a more efficient solution. And this is something that's fairly common when we look at how people think. If you've heard of the concept of thinking fast and thinking slow, where fast thinking is when we rely on heuristics or shortcuts. So this has worked in the past, we're just going to blindly apply it, and if it works, we just keep going, we don't check our work. Slow thinking is more like taking our time, actively thinking about the process, maybe overriding some of our gut instincts, and it allows us to find more creative solutions, possibly more efficient solutions, but it is more resource intensive and takes a lot more time and effort. So you can have those two types of strategies. But if we think about it, if we encountered problem B, the second problem, first, we probably would have found that faster solution first. But our pre-exposure to problem A is what led us to try that other strategy. And for questions like this in different studies, they'll present it A then B for some people, B then A for others, and look at which strategies they tend to rely on so that we can see that reliance on prior experience and how much it's affected by that prior exposure. And if we want the technical term for that existing solution that we're kind of stuck with, it's also called a mental set. So that's our expectation of how to solve a problem given that prior experience. So our mental sets can influence how we approach a problem. And the getting stuck can also be called fixation. So you can get stuck in one of those dead ends of, well, this solution has worked before, so I have to try this solution or something similar. And you might overlook a simpler, more accurate response. So yeah, those past experiences or our expectations of what should work can influence our approach and prevent us from finding the correct response or correct solution if we get too focused in on it. And similar to that fixation, we can actually have the concept of functional fixedness, where we're not necessarily stuck on the solution itself, but this is when we get stuck on the function of an object that's part of one of our puzzles, part of one of our problems to solve. And so this is our tendency to view an object as having only one function, and that one function being the one that it is commonly used for, and neglecting using it for an atypical purpose. And the example here, if you're wondering what the heck does a box with candles, matches, and thumbtacks have to do with functional fixedness, this is actually another example testing that process, where they would provide people with a box full of matches, a candle, and some thumbtacks, and they would say, you need to get this candle away from the table so that while it's burning, it doesn't drip wax on the table. And so if you give them all of these objects, people will typically take those thumbtacks, and if the table has, say, a bulletin board next to it, they'll start trying to prop up the candle against the bulletin board to make sure that while it burns, it A, doesn't burn the bulletin board, but also B, does not burn the table. However, if you give them those items outside of the box, they now no longer view the box as a container and now view it as a tool that they can use. So they would just stand the candle in the box and light it because the box prevents the wax from touching the table. And so this process, this sort of fixation on the box is a container, it's not part of the thing, it's just holding the pieces that we're using for this task. As soon as we get around that, we can now solve the problem possibly more efficiently. I find this is one of those things where I don't tend to fixate on function, which drives people nuts because I propose odd and obvious solutions. Like my partner was looking for a hammer, couldn't find a hammer, was losing his mind. And I'm like, well, a wrench is heavy and also metal. Why not just use the wrench? It's putting a small nail in drywall, like it's going to serve the purpose. But that hadn't occurred because wrenches are not used for hammering. Hammers are used for hammering. So people can get stuck, once again, with this is the thing that I need or this is the solution that I need and miss some other solution that could be proposed. Our next little section here is a couple of important terms on some of the strategies that we can start using. So the first of these terms is an algorithm, which you've absolutely heard this word in a whole bunch of different contexts, but for our purposes, an algorithm is just a precise set of rules that we're going to apply in a strategic order so that we can solve a problem. So if you have, you're playing a video game and there's a safe and there's a 4-digit code to get into this safe. And you could run off and do a whole bunch of fetch quests and someone will give you the combination, or you could figure it out. You start with 0, 0, 0, 0. No. Okay, 0, 0, 0, 1. Okay, 0, 0, 0, 2. And that would be an algorithm. You would absolutely find a solution in the end. Is it the most efficient strategy? Probably not, but you are guaranteed a solution. So an algorithm, it has those sets of rules, it has that sort of specific order that you're testing, but it can be resource intensive or time as a resource as well. It can take a really long time to find that solution. You might opt for trial and error. And this is when you're going to try a bunch of sequences, maybe at random, until you get the solution. So this would be, okay, well, instead of starting at 0, 0, 0, 0, I'm going to start with maybe familiar numbers. Maybe I'll go with a bunch of birth dates or whatever numbers I want to try first, and I'll write them down as I go. So there's no set strategy, no rules for the order that you're using. You're just trial and erroring it. Here, this at the bottom is one of those other strategies that are problems that people will tend to pose. So they have one of those situations. You have a boat and you have 6 people on one bank and you want everybody on the far side. However, the boat can only ever hold 2 people, and you want to make sure that nobody is ever left outnumbered on the opposite shore. So you don't want to have, say, 2 orange and 1 green, because the 2 orange people will beat up the green person. And there's tons of different iterations of this. I've seen versions of it where they do orcs and hobbits, or sheep and wolves, or whatever it is. But they're all, here is our start point. Here is our end goal, that goal state, and here are restrictions on what can and cannot happen in that process. And so, if we trial and errored that, we could technically say, okay, I'm going to guess. We're going to start by bringing one of each color to the other side, and then we're going to bring one of them back so that I can move these people next. And you can sort of start working it through that way using just whatever you think is going to work. Alternatively, you could start at the beginning and say, okay, well, first step, 2 oranges are the first on the line, they're the first 2 to the other side. Wait a second, that doesn't work, the 1 orange was left, so we have to try something else. Next strategy, but you'd have rules for which approach you take. We also have a concept called heuristics, which I mentioned in advance because I never remember what I have slides for. Heuristics, we can just call them our shortcuts, our rules that we have already existing that we can apply to solve these problems. So once I've learned that solution for problem A worked in that instance, we applied that rule set to problem B and it worked, therefore we moved on. So you can have prior experience give you these ideas of how you could solve. And like I said, heuristics are typically sort of that quick and dirty solution of it's worked in the past, it might not be the best solution, but if it works, and we can continue. We'll also see the concept of heuristics applied for a lot of other contexts. So this word will keep coming up in other chapters, but we'll talk about it as ways that we tend to think about even, say, groups of people or different concepts as a sort of quick and easy way to react in a situation where we might not have a lot of information. So you can relate heuristics to things like stereotypes, which in psychology, a stereotype isn't necessarily a bad thing. The way it's defined is that a stereotype is just a heuristic, a shortcut for thinking about a group before we have information regarding individuals within that group. And the example I always use to apply that is teaching to a class. So I have a first-year class. I have a base assumption of this is how much experience you have with certain words and terms. I don't have more information than that because I don't get to interact with everybody, but I'd say, okay, if you email me and you're from this class, I'll give explanations at a first-year psychology level. However, if a student then replies and they clearly have experience in this field, maybe they have a related degree or practical field experience or a personal interest, and if they are then able to use more complicated words, I can now say, okay, my stereotype got me started. I reacted in the best way I could with limited information. I can now adapt and match to this person. So I can respond at their level instead. So you make those adjustments as you gain more information. So heuristics could also be a starting point. So like with our problem B, if we tried our prior solution and it didn't work on a new problem, we might then try some other strategy. So it's a start point, and it might get us the right answer, it might not, but we're acknowledging that it's a shortcut and has those limitations as well. And of course, there are some specific heuristics that we can talk about. The first of these is our means-end heuristic. And this is when we're specifically looking at the end goal. And sometimes you might even use this means-end heuristic to work backwards from that end goal. So you might start with, okay, well, if this is where we need to end, with our example with the boat, if we know what our end is, maybe we work in the opposite direction. This one, I believe, has to be symmetrical, so it doesn't necessarily help you out, but we're focusing in on what that end goal is, and that's your priority. And you're going to choose possible solutions, you're going to choose your strategies based on what is most likely to get me to that end goal. A little bit more interesting, we can get into the representative heuristic. End of a long day, and this is when a problem solver is mentally comparing something to some stored prototype of an event or object or person. So you're thinking about this problem and comparing it back to that representative prototype. How close is this situation to what my idea is of this typical problem? So we might assume that something belongs to a particular category because it seems like it's similar to that prototype. I will try this particular strategy because it worked for something similar in the past, but if this current event is actually not all that similar when you dig beneath the surface, that might not help us solve the problem. So we can end up with bias if we make assumptions about it belonging to a particular group just by looking at likeliness or shared qualities to a prototype event. It can be beneficial because if there is actually a link, if it does fall into that category, then we've sort of eliminated other non-solutions and we're focusing in an area that might actually help us. But it could also lead to errors in problem solving if our initial assumptions are incorrect. And then the last one is my favorite of all of these, and this is the availability heuristic. And this is a rule of thumb where we try to accurately estimate frequencies of behavior or of events, but we actually use how easy or difficult it is to remember that event occurring in our recent past to make that estimation. Basically, if something sticks out in your mind, you assume that it's very likely to occur. So typically, people will use the example of how common it is to die by shark versus vending machine. And you've probably heard the example, and more people talking about death by vending machine as being disturbingly common might have raised your understanding of how likely it is. But typically, the thought of shark attacks tends to be something that's a little bit more visceral and therefore easy to remember and causes that sort of emotional response. But also anytime it happens, it usually gains media attention and therefore it's talked about for a while. And so that awareness that, hey, I remember someone mentioning that recently makes us think that that happens a lot more often than it really does. Whereas if somebody is injured by a falling vending machine, that tends not to make the news, and it tends not to be talked about for long periods after it's happened, and therefore people underestimate how likely that is. This can also just be a timeline thing. So with personal experience, if within your frame of reference, so say you have a group of friends, you have 10 friends, and of them, 5 of them have divorced parents, you might assume that that is the same as the national average. 50% of people must therefore have divorced parents. But it's all based not necessarily on actual data or actual studies or anything like that. It's just based on what it's easy for us to think about, what it's easy to recall. So it's all about what's available for our thought process. And we make our determinations in that way. And obviously that can be very much biased because experience is not a great equivalent for actual data. All right, how are we doing? I'm just gonna double check how close we are to the end here. Okay. So we'll talk a little bit about the next couple of slides here where we're looking at creativity and some of these factors that might be involved in creativity. So when we're trying to become familiar, or trying to solve a problem, we might start off with our preparation stage of what is the system that we're looking at? What are the rules of the problem we have to solve? This example is obviously using chess. And so we might say, okay, how would we move these pieces to get them into this particular arrangement? And you'd have to maybe know the rules of chess and how different pieces move. You might have to know some other aspects that would get you that solution. So step 1 is becoming familiar with a particular problem. We then typically have that, okay, we've gathered our information, we understand the system, we understand the rules, we know what's going on, we know what we have to do. Then we're going to take a break. Incubation is that process where you're kind of mulling it over, but not actively trying solutions. So this is kind of an interesting process because sometimes you end up doing better on solving a task if you can step away from it for a little while. So if you've ever had that moment of, holy smokes, I know exactly what I need to do, when you've woken up from, say, a deep sleep in the middle of the night, and you've been mulling over what your final sentence needs to be for your essay, and you wake up and you know exactly what it has to be. Or you've been trying to solve a technical problem, if you're like me and tend to cause issues with electronics, and you've been walking away because I cannot try different combinations of turning things on and off again, and then you're washing the dishes or having a shower or something like that, and you go, I need to try this. That incubation period, that stepping away, can be really, really helpful. And we could say also that that aha moment of it finally came to me is actually our third state, that illumination state of insight where we've suddenly realized the solution to our problem, or at least a potential solution to your problem. You could then go and evaluate that. Is this a good solution or not? I tried my on and off combination that I just thought of. Does it work or not? If yes, fantastic, walk away, problem solved. If no, we might have to maybe familiarize ourselves or go back to ignoring it until something better occurs to our minds. And I've been jumping back and forth over this here. This was just sort of some theoretical data looking at individuals who were given a series of tests. So they tested them on certain information they had absorbed and then followed up with either an easy test or a difficult test. And they looked at what they were doing in between the first test and the second test, where we see here that there's an interaction effect. Specifically, having an easy test means that there's not a difference between our groups, really. A little bit here with the sleep. But if it's a hard test, if there are difficult concepts to learn, taking a step back and sleeping on it ended up actually facilitating their problem-solving abilities. They performed better answering complicated questions if they were able to sleep on the information after learning it. So this is just one example of how that incubation process could be beneficial. You don't need the specifics, obviously, of the study because I'm not giving them. But we're just getting, this is a thing that can occur. And then we are so close to the end. I think we can do it in 5 minutes. Let's try it. Of course, we've mentioned a little bit about bias and the fact that we can have biases in a lot of different areas within psychology. Decision-making is not, it's not an exception. So confirmation bias, and we talk about it here, but it applies to other areas. It actually could have been brought up in our methods section, but confirmation bias is our tendency to only pay attention to evidence that supports our original position. In this situation, if you have an existing theory, you have an idea of something that should be a solution or this should be how this works, you tend to ask questions or search for information in a way that gets you confirmatory information. So maybe you have a theory that X causes Y, and you might go to Google and say, papers where X causes Y. Well, now you've excluded papers where they are unrelated or they have an opposite relationship. So we're ignoring information that goes against what we thought, and we prioritize information that matches with what we think. And we do this not just in scientific literature, but we'll also do this when we're, say, when we're asking questions or talking to people. We tend to, say, talk to people who tend to support our ideas, tend to go along with how we think. So you can end up with that confirmation bias in sort of social interactions as well. We mentioned before framing as that way of how we take information and frame it or put it into something that we could solve. Word problems are a great example of this, where framing depends a lot on how we think about this information. And you'll typically find that framing can be important in those train and distance type questions because they often give you useless information or information that isn't actually necessary to solve the problem. But a lot of people frame the problem requiring that information. So you have to think about what does and does not need to be included and how does it all relate to the situation you're trying to solve. We can also look at framing for decision making because we tend to have biases in what we tend to prefer. So if you have the exact same proposed question, would you rather for sure save 20% of the population, or would you rather for sure kill 75% of the population? People are always going to choose the sure win, the sure save. And even if you frame it exactly the same in opposite directions, we take a sure thing for gaining, and we tend to gamble to avoid risks. We tend to prefer certain terms and certain words when we think about what's the preferable outcome in these situations. And clearly we're not going to end up, oh, actually, that's not the last slide. Of course it's not the last slide. Okay. I'm not going to rush this. We'll come back and we'll finish this slide and the specific example, and then we'll start the next chapter next time.